In this lecture, we will look at flow in elastic tubes. Until now, we have been looking at different variations of flow in rigid tubes. So, as we know that the cardiovascular system is a network of flexible tubes which have different sizes. So, we have looked at flow in rigid tubes because as an approximation, the flow in rigid tube can give quite significant amount of information about flow in the cardiovascular system. We have also looked at pulsatile flow in rigid tubes. Now, in this lecture, we will relax the assumption of rigidity and try to understand the flow in elastic or flexible tubes. So, there is a difference between flexible and elastic tubes because elastic tubes are the ones which strictly follow Hooke's law, which is not necessarily true for the blood vessels. But as an approximation, in this lecture, to make our equations and mathematics simpler, we will primarily look at the flow in elastic tubes and use Hooke's law to understand or relationship between stress and strain for the solid tubes. So, until now, as the course is on cardiovascular fluid mechanics, we have been focused on the flow part of it and did not bother about the mechanics of the solids or mechanics of the channel walls. But in this lecture, as the flexible nature of the channel comes into picture, then we also need to take into account the forces that are being exerted on the walls of the channel and the resultant deformation on the channel walls because of or as a result of the forces that are being employed or that are being exerted on the walls of the channel. So, to understand this lecture, we need to have a background or we need to have a little bit of understanding of solid mechanics as well. The primary understanding that we will be requiring or we will you will need to go back to your solid mechanics lecture in first year undergraduate or second year undergraduate course. The primary understanding is required is in terms of stresses or hoop stress or circumferential stress in the circular or cylindrical channels. That is what we will be using in this, and these channels or walls of the channels are thin wall tubes. So, hoop stress or circumferential stress in the thin wall tubes, that is the solid mechanics topic that will be used here. We will be deriving the relationship, but for the clarity's sake, I would request you to look at those chapters. So, in this lecture, we will consider two cases. The first one where the flow is steady, that means the flow does not change with time. A special case of this for fully developed flow is Pulsatile flow, but Pulsatile flow is flow in a rigid tube. So, we will first look at the steady flow in a rigid tube, and then the next extension will be that we will relax the assumption of steadiness and consider pulsatile flow in a rigid tube. But for pulsatile flow, we will relax or we will have another assumption that we will assume the flow to be inviscid or the flow to be non-viscous. That means, if you remember the definition of Vommelslee number, this is true for large Vommelslee number. Okay. So, let us look at the first case when the flow is steady in and it is laminar in elastic tubes. So, as you can see here, initially these are the boundaries of the channel. So, if the channel is cylindrical and there is no flow, then there is no deformation in the walls of the channel. The pressure inside the channel and outside the channel both are same. So, let us say that the values of the reference pressure is 0 at the external pressure and 0 internal pressure. When the flow happens, the external pressure is not going to change, but because the flow will be pressure driven, so there will be a gradient set up in the channel, and pressure at the upstream or at the inlet will be higher. Let us say this pressure is P0, and at the exit or after length L, this pressure is PL. External pressure is still 0. So, what will happen as the pressure will decrease downstream, the forces or the total pressure being exerted on the channel wall will vary. The external, because the external pressure is same and the internal pressure is decreasing. So, as we move downstream, the pressure on the tube walls will be more, and because of that the tube diameter will change, and when the tube diameter changes, that it keeps reducing. Okay. So, we have two problems, as I said, we have fluid mechanics problem and solid mechanics problem. So, for this simpler case, we will take an iterative approach and solve the fluid mechanics problem and solid mechanics problem sequentially, iteratively, until we reach a converged solution. So, first we will solve the fluid mechanics problem. We consider that this tube is rigid tube and the wall shape is specified, and at the first iteration, at the very first iteration, we can consider that the channel radius is same everywhere and it is a cylindrical channel. So, for this tube, rigid tube with the specified wall shape, we calculate the pressure distribution for the given flow rate. So, the simplest problem that we have considered, which can be valid for small deformations in the channel, where the radial direction velocity in the radial direction can be neglected, and the assumption of del u by del x, that is the gradient of velocity in the axial direction, can be neglected. Then we can calculate the pressure distribution for the given flow rate very easily using Poiseuille's law, because that will still be valid. So, we can calculate using fluid mechanics what is the pressure distribution for the given flow rate. But for the cases where these assumptions are not valid, for that also it might take some more mathematics or use numerical methods to solve the flow, but we can solve the pressure distribution for the given flow rate and can also get the velocity distribution. Now, we come to the solid mechanics part and we consider the tube to be elastic and calculate the deformation. So, we can, for the given flow rate or for the given average velocity, we have calculated pressure distribution from here along the length of the channel. Now, from this pressure distribution, because we said that the external pressure is constant, now we will consider the tube is elastic and calculate the deformation. Okay. And from this deformation calculation, we can calculate the shape of the wall because of this force distribution or because of the pressure distribution as a result of the flow, and from this deformation what is the shape of the wall. Now, once we have calculated the wall shape, we need to see that has the shape of the wall changed from step 1. If it has changed, then there is a bit of mistake here. Has the tube wall shape changed? If yes, then we need to go to again step 1 and recalculate the pressure distribution and go through step 2, 3, 4 and come to 5 again. If it has not changed, if the wall shape has not changed, then we do need to go to next step where the final solution has been obtained, that the solution from the solid mechanics and the fluid mechanics, they are consistent. So, let us try to do it for a simpler case where we assume the Poiseuille's law to be valid. So, we will need to make some assumptions to do that. First, we consider that the tube is very long and the entry and exit effect can be neglected in the tube is cylinder. Now, the flow is laminar and steady, that is anyway the assumption in this part of the problem. Then we have neglected entrance and exit effects. We also assume that with the deformation there are changes in the shape of the tube, but the inner surface of the tube, it remains smooth and it remains cylinder even after the deformation. So, in such cases Poiseuille flow is a good approximation. What are the assumptions that we will need to make mathematically here? We are saying when we use Poiseuille flow that VR is negligible, then V x is almost 0 in this case. So, from our previous lectures you might remember that Poiseuille flow is the pressure gradient is equal to minus 8 mu by pi a to the power 4 q, where q is the volumetric flow rate and A is the channel radius. Now, A is not a constant here. So, that is why we have said that A is Ax, which is a function of x. Okay. So, if we know the relationship between P and A, then we can integrate it. So, let us say dP is equal to minus 8 mu q over pi, because flow rate is a given quantity. So, we will take it to be constant and this will be dx over Ax to the power 4, and that can be at x is equal to 0 to some x, and similarly pressure can be at P0 and Px. So, the requirement for this is that we need to know what is A as a function of x. Now, let us look at, as I said at the start of this lecture, that we need to look at a small part of solid mechanics where we are trying to find the relationship between hoop stress and the pressure for a thin wall tube hoop stress or circumferential stress. So, the stress that is being exerted in a thin wall tube, we assume that these stresses are, or this stress is sigma. For simplicity sake, we consider a semicircular portion of the tube, but one can also consider a small arc of the tube, but the involved algebra there might be a bit cumbersome. So, to simplify our algebra, I have considered the semicircular part of the tube, and as earlier we have considered that the external pressure on this is equal to 0. The radius of the channel, let us say that this is A, and the small length of this channel that we consider or that we can consider is say dx. Now because of the pressure, the normal force, if we say that this is y and z direction, then the force in y direction will be P into the projected area in the y direction. So that projected area of the tube in y direction will be 2a, which is the diameter of the channel multiplied by the length dx. So this area, the projected area in the y direction of this tube surface is going to be a rectangular area. So the width of this is 2a and the length is dx, and on this area the force that is being exerted in the y direction, that will be P into 2a dx. Now this pressure will be balanced by the hoop stress which will be exerted on the tube. So this hoop stress, if we say that H is this thickness, and remember that we have also assumed that the tube is thin, so we need to say that H is very small than A. Under those circumstances only this analysis will be valid. So this is equal to sigma into H, the area of this tube wall on which this stress is being exerted is H into dx, and we have two such surfaces, so this will be multiplied by 2. Now dx will cancel out, and we can also cancel out 2. So we have a relationship that P into A is equal to sigma H. So we can say that sigma, or the hoop stress or hoop or circumferential stress, that is equal to Px Ax over H. Okay. So that is the formula for the hoop stress. Now we can use Hooke's law for thin wall tubes. So Hooke's law, you might remember that it is valid for perfectly elastic material, which says that the deformation E is equal to sigma over capital E, where capital E is the modulus of elasticity. And now in the circumferential direction, what is E? E is equal to the change in the circumference of the thin tube. So that will be 2 pi A x minus 2 pi A naught divided by 2 pi A naught. So A naught is the tube radius at the inlet or initially, and after deformation the tube radius is Ax. So if we cancel out 2 pi, then E will be Ax minus A naught over A naught. So we can substitute from Ax minus A naught divided by A naught is equal to sigma over E, and we can substitute sigma from our previous slide where we obtained a relationship for hoop stress, that is equal to Px Ax over h, where h is the tube thickness. So we will have that Px is equal to, that is, there is we have E also, so that will be EH over AX into AX by A naught minus 1, or EH over A naught, we take AX by A naught out, so this becomes 1 minus A naught by AX. So that is one relationship for Px. Or we can also change this into a relationship for Ax in terms of Px. So we can take both the terms containing Ax on one side, which will give us Ax by A naught minus Px Ax over EH is equal to 1, and if we take Ax by A naught outside, then we will have 1 minus Px A naught by EH is equal to 1, or we will have Ax is equal to A naught 1 minus A naught by EH Px, and because it has been taken on this side, so whole to the power minus 1. So we have a relationship between Ax and Px. Now we can try to substitute this relationship in the Poiseuille equation, which is the relationship between Ax and Px is this, and the Poiseuille equation, you might remember, was dP by dx is equal to minus 8 mu over pi Ax to the power 4. So we can substitute this relationship here, pi A naught to the power 4, and this will go up, so we can have 1 minus A naught Px over EH whole to the power minus 4. So 8 mu pi A to the power 4 into Q. So we can bring Q here. Q is the given flow rate. Now this differential equation, this is a differential equation in Px. We have eliminated A successfully from here. So we have only two variables here, P and X, and we can integrate it. So this is, this is going to be plus because we have taken this up in the numerator. So this becomes, now we have to do a bit of algebra, and 1 minus A naught Px over EH dpx is equal to minus 8 mu q by pi A naught to the power 4 dx, okay, and integrate it from x is equal to 0 to, we can say, L, and similarly this will be P0 and PL. So we need to know the difference between these 2 points. Okay, this will simply be minus 8 mu q by pi a naught to the power 4 into L, whereas if we want to integrate this, we can simply integrate it. Let us say that t is equal to 1 minus a naught px over EH, and that will give us dt is equal to 1 minus that 1 will go away, and we will have simply minus a naught by EH dp. Okay, so let us substitute this here, and what we will obtain is 1 minus a naught px EH becomes t, and dpx will be dt multiplied by minus EH by a naught into dt. This is equal to minus 8 mu q over pi a naught to the power 4 L, and this is P naught. So at P naught this becomes 1 minus a naught P naught over EH, whereas at PL it becomes 1 minus a naught P at L over EH, and that there is a mistake of power that we have left here. That was power to the power minus 4 that was supposed to be. So this is t raised to the power minus 4, and now we can substitute this and say this is minus 8 mu q L over pi a naught raised to the power 4 is equal to minus EH by a naught, then t to the power minus 5 divided by minus 5. So we will have 1 over or minus 4 plus minus 4 plus 1, so t to the power minus 3 divided by minus 3, so minus 1 over 3 multiplied by t to the power minus 3, and we will have 1 minus a naught PL over EH, this raised to the power minus 3 minus 1 minus a naught P naught over EH raised to the power minus 3. So this equation does not come out to be a simple one, but still we have managed to solve this equation successfully for a elastic tube. And if we go back and look at what is the relationship between A and P, this is not a linear relationship. Okay, and AX PX A is about, not exactly, but about inversely proportional to PX. So let us go and look at another. Okay, so we have looked at what will be the relationship for steady laminar flow in an perfectly elastic tube. Now, as I said at the beginning, that the blood vessels, they are not exactly, they do not follow the Hooke's law. So they are not perfectly elastic tube. They have some amount of viscoelasticity, but we will not go in detail of the properties of the elastic, or the properties of the vessels of the channel. We will not go in great detail of that. We will just assume another relationship between P and A, and this time a simpler relationship which is linear. So, this form is Ax is equal to A naught plus alpha by 2 Px, where alpha is the compliance coefficient. So, we can consider this linear relationship between Ax and Px. Now, in this linear relationship is generally valid for certain category of arteries, which is pulmonary arteries, the arteries which are in the pulmonary system. For that, this relationship is valid. So, we will try to look at the relationship, and this is the final expression that one can derive. Okay. So, we had this relationship dP by dx is equal to minus 8 mu over pi 8 to the power 4, where Ax. So, we will write this as Ax to the power 4 into Q. Now, from this we can say that dA by dx or dAx by dx is equal to alpha by 2 dP by dx. So, we can substitute this dA by dx from here. So, we will get 2 by alpha dA by dx. For simplicity's sake, we will write only dA by dx, and we will not write A and x in the bracket. So, 2 by alpha dA by dx minus 8 mu q over pi a to the power 4, and if we do a bit of algebra, a to the power 4 dA is equal to minus 4 mu alpha q over 2. So, that is 2 has already been taken care of, divided by pi and dx. Okay. So, let us now integrate it from 0 to L. All these terms are constant, so we can take them out of the integral sign, and this is from 0 to L, and this is from A0 to AL. So, that will give us A to the power 5 divided by 5. So, we can take that here on the other side, or we can, let us say, we can put that as 1 over 5 AL raised to the power 5 minus A naught raised to the power 5 is equal to minus 4 mu alpha q over pi into L. Okay. So, if we take this here, we will get this relationship. Minus can be brought here. So, A naught 5 minus AL to the power 5 is equal to 20 mu alpha L over pi q. Okay. So, what we can see from here, that A naught to the power 5 minus AL to the power 5 is proportional to the flow rate. Now, if this is the case, let us say if the change in radius has become AL by A naught is equal to half, then as a consequence of this, mu is a constant, alpha is a constant, compliance coefficient, L is constant, pi is constant. So the flow rate is going to change. So if we look at this, and AL by A naught is 5, then AL by A naught to the power 5. We can just write this in terms of the ratios probably. A naught to the power 5, 1 minus AL by A naught to the power 5 is equal to 20 mu alpha L over pi Q. So if this is 1, then this number will be 1 over 2 to the power 5. So 2 to the power 3 is 8, and that will be about 8 into 4, 32. So only about 1 over 33, so only about 3%. So the radius will remain, or the radius of the channel will be only 3% of the inlet radius, so which can be neglected in those terms. So basically Q for channel radius half of the initial radius or more, Q will be almost proportional to A to the power 5 rather than, because AL to the power 5 is going to be very, very small. So this number is going to be very small, so that is directly proportional to A to the power. This is when there is linear relationship between the A and P, where A is the channel radius and P is the pressure variation along the channel. So what we have looked at is, at the first problem, steady flow in a channel. First we had our relationship between pressure and flow rate from fluid mechanics, and we simply assumed Poiseuille's flow under certain conditions, which, and then based on that pressure distribution, we calculated what is the deformation in the channel, or what is the change in the channel radius, and then we substituted this channel radius in the Poiseuille's flow and calculated the flow rate. So this problem, in this problem we had to consider both the fluid mechanics problem, which is Poiseuille's flow, and the solid mechanics problem, where we looked at the deformation for a thin wall tube. Okay. Now we will look at the second problem, which is pulsatile flow in the elastic tube. So for pulsatile flow in the elastic tube, we will make certain assumptions and look at only a very ideal case. We assume that the channel is infinitely long, so no entrance and exit effect are being considered here. The channel is, or the tube is isolated with other system, and the external pressure remains constant throughout. We are not considering the changes in the external pressure. The system is isolated, right, and the cross section is circular and the channel is cylindrical, and it is an elastic tube. So we will consider that the tube follow Hooke's law, and again we will use the relationship between sigma and P, or between A and P for a elastic tube that we just obtained in the previous problem. Okay. And then we assume that the fluid that we are considering, unlike the previous problem where we considered the flow to be laminar, here we will consider that the flow is inviscid. That means the viscosity is 0. So the velocity profile is going to be same I mean it will be uniform flow or plug flow. Another assumption is that the wave amplitude is small. So, the amplitude of the pressure wave that will be generated will be small, and the wavelength of this wave is very large or sufficiently large than channel radius. So, the wavelength is large or the channel radius is very small than the wavelength. Okay. This is called long wave approximation, and this makes sure that the slope of this deformed wall is less than 1 or very less than 1. So, there are only very small changes, and under these conditions we will be able to linearize the equations, because in this case we will have non-linear equations which is difficult to solve. So, we will try to linearize the equations, that is why we are trying to make these assumptions. And the flow is one dimensional. So, we consider that when the flow is one dimensional, V r is equal to 0. Okay. Now, under these assumptions, when there is a deformation at one point of the tube, there will be a pressure wave generated on the tube, and this pressure wave will travel on the channel wall. So, we need to get the speed of this pressure wave or pressure pulse. So, the objective here now is to obtain the speed of this pressure wave, and then eventually we will obtain a wave equation which can be solved to find out the pressure profile as well as the velocity profile, or pressure as a function of x and t and velocity as a function of x and t. Okay. But in this problem that we are going to deal with here, right now we just want to solve, or we do not want to solve the equations, we will write down the equations for this simpler case and try to obtain a relationship for the wave speed or the pressure pulse speed and the equation that govern the pressures. So, as always we will start with the conservation equation. So, let us look at the force balance or the momentum conservation equation. So, we can write m into A, where we have considered a small part of the fluid element here, you can see here, and in this case the area is changing and the length of this fluid element, let us say this is dx. The area at starting point is A and at end point is A plus del A by del x dx. Pressure at the left end is Px, and then at the right end it becomes Px plus del P by del x dx, and at the two ends you will have a pressure as Px plus del P by del x, if you want to consider this at these points, then you can consider as a dx by 2, and similarly on the other side. So, if we write down the force balance m into A, so that will be m is rho into V. V is the volume of this fluid element. So, A into dx, the area of cross section, into dx, this into the acceleration del u by del t plus u del u by del x. So, we are not going into detail of derivation of this acceleration, we can directly consider this. this is the unsteadiness or the acceleration, and this is the convective acceleration. Now we will consider the forces. So the force, because the flow is happening from left to right, so we will consider the force Px into A. Remember that A is also a function of x, but we are not going to write that here, and we will write P also simply as P, not as Px. So Pa from left to right minus P plus del P by del x dx into A plus del A by del x dx. So these are the forces that are acting on these two ends, and the third force, that will be also because of pressure, that will come the total sum of these two pressures acting on these walls. So that will be the projected area multiplied by the pressure. So neglecting the higher order term, we will have this as Px into del A by del x into dx, the entire using these two. So now let us expand this and neglect the second order terms which are there. We can also maybe we can retain this as of now, rho A dx del u over del t plus u del u over del x is equal to Pa minus Pa minus A del P over del x dx minus P del A over del x dx. The multiplication of these two terms is going to be a second order term, which we are going to neglect anyway. So plus, so I am not going to write that, plus Px del A by del x dx. So Pa will cancel out. I will just write here higher order term. I have only limited space, so I need to save some space here. And this is P. I should have avoided writing Px here, so we will just write this as plus P, and this will cancel out. So now we see in these two equations A dx will cancel out. So what we'll obtain is, and del u by del t plus u del u by del x is equal to minus A dx over rho A dx. So we will cancel out this A dx and A dx, and what we will have is minus 1 over rho del P over del x. So this is our force balance or momentum equation, del u by del t plus u del u by del x plus 1 over rho del P by del x. Remember that this is the term which have non-linearity. Here we have multiplication of u with u. So this is the non-linear term in this equation. Okay. Now next we consider mass balance here. So again for mass balance, as earlier, this length is dx, and the flow that is coming from here is, say, volumetric flow rate is UA. Because this is an incompressible flow, so the density will cancel out, density will not have any effect. So if the mass flow is conserved, then rho, because del rho over del T will be 0. So we can take rho out if we want. We may take it out, and here what we'll have is UA plus del by del x of UA. So mass balance is the accumulation, and the important thing here to note is that volume is also changing. So we can say that del over del T of A dx, right? The change in volume is equal to U A minus, this will be del U by del, U A minus del by del x U A dx. So this UA will cancel out, and what we are left with is del A by del T dx is equal to minus del by del x UA, or after substitution del A by del T plus del by del x UA. Now U and A both are functions of x, so this term might have some linearity into it, we will look into now. So now let us linearize the two equations. To linearize, we will need to make certain assumptions under which these linearized equations or these equations can be linearized, or the linearized equations will be valid. Okay. So we assume that the blood velocity U is small, the pressure difference, the pressure difference between internal and external, that is small, and area change, the change in the area, if the area is A naught at the entrance of the tube, or at the start, and A is the area which is changing with the distance, then this area change is small. So A minus A naught or A naught minus A is small, and the derivative of all of these, del U by del x, del P by del x, and del A by del x, del capital A by del x, they are all small. So we assume that, and under these assumptions we will try to simplify the equations. So the force balance equation, we will just go back and look at the equations. The force balance equation was del U by del T plus U del U by del x plus 1 over rho del P by del x is equal to 0. The mass balance equation was del A over del T plus del over del x of U A is equal to 0. So these are the two equations, and now we need to linearize this. The force balance equation, if we look at, this term is the non-linear term, and it is multiplication of U, which we said is small. Its value is of the order delta, and del U by del x, which is again small. So this term is going to be of the order of delta square, whereas other terms will be of the order of delta, for example del U by del T and del P by del x. So they are of the order of delta. So this term can be neglected. Okay. So we will end up with del U by del T plus 1 over rho del P over del X is equal to 0. Now we look at the mass balance equation, which is del A by del T plus, let us expand this, U del A by del X plus A del U by del X is equal to 0. Again, this term will be of the order of delta. This will be delta into delta, and A is large anyway, so we cannot say that what is this going to be. If A is say of the order of 1 and del U by del X is again delta, so this term is going to be small in this case, and we will have to neglect this. Another thing here is that because this term is again it bring non-linearity, because A is a function of x and U is a function of x, so what we can assume here that A, the change in age is small, so we can assume A is almost equal to E naught, so that will give us del A over del T plus A naught del U by del X is equal to 0. So we have our linearized equation del A by del T plus A naught del U by del X is equal to 0, and del U by del T plus 1 over rho del P over del X is equal to 0. So now what we will do is obtain a relationship between second derivative of del 2 U by del X del T from both of these equations and equate the two. So if we do that, from here we will get del 2A over del T2 plus A naught del 2U over del X del T is equal to 0. Similarly, from here we will have del 2U over del X del T. You might remember that you can write this as del X del T or del T del X. It does not make any difference, but just for the clarity's sake, I have written in this manner here: del 2U by del X del T plus 1 over rho del 2P over del X2 is equal to 0. So if we, from these two equations, if we equate the two values of del 2U over del X del T, then what we will get is minus 1 over A naught del 2A over del T2 is equal to minus 1 over rho del 2P over del X2. Can compare these two terms, and what we get is these two equations. From this we get del 2A over del T2 is equal to A naught over rho del 2P over del X2. So remember, what we have been able to get is a relationship is the double derivative of area with respect to time and double derivative of pressure with respect to distance, and this is based on the flow equations only. Now we will go back to the solid mechanics equation, the relationship that we obtained between pressure and the radius for a thin tube. So, if we write this in terms of the area, then it will be EH over A naught into 1 minus A naught over A raised to the power 1 by 2. We will keep A naught intact here, and this ratio is A naught over A raised to the power 1 by 2. If we now linearize this equation, then we will need to use A naught by A is equal to, we can write A naught plus A minus A naught, or A naught by A. So, we can write A plus A naught minus A divided by A, or this will be equal to 1 plus A naught minus A over A. So, using binomial expansion, we can write this A naught by A power 1 by 2 is equal to 1 minus A naught minus A divided by A raised to the power 1 by 2. So, that will be 1 minus 1 by 2 A naught minus A by A, and higher order terms. We know that A naught minus A is where can be neglected as A naught minus A over A is very small than 1. So, we can neglect the higher order terms. Okay. So, if we substitute that here, we will end up with Px is equal to EH over A naught into 1 minus 1 by 2 1 minus 1 plus 1 by 2 A naught minus A over, sorry, I have done a mistake here. This should have been plus, this should have been plus, and this should have been plus. So, if we do that, then this would have been minus. Okay, 1 and 1 cancel out, and we have Px is equal to EH by A naught into half A minus A naught over A, but so this is A, but as A is the difference between A and A naught is very small, and we want the equation to linearize, so only linear relationship between P and A. So, we will have this A is equal to A naught. We will just write here that A is almost equal to A naught. So, that is why this has come up. AH by 2 A naught, capital A naught, A minus A naught. Okay. So, Px is equal to EH over 2 A naught, capital A naught, A minus A naught. That is the relationship between pressure and the area that is coming from the solid mechanics, and we can double differentiate this equation. Actually, the equation Px is equal to EH by 2 A naught A naught. So what we can get from here, del P over del T is equal to EH over 2 A naught, capital A naught, del A over del T, and the second derivative will be del P2 over del T2 is equal to EH over 2 A naught, capital A naught, del 2A over del T2. So EH by 2 A naught, capital A naught, that's what we need to remember. So we will just write the equation del P2 over del T2 is equal to EH over 2 small a naught, capital A naught, del 2A over del T2. This is the equation that we obtained from the solid mechanics, and this is the equation that we obtained from the two mass and momentum conservation equations. And if we equate del 2A by del T2 in both the terms, then we will have A naught by rho, or we can substitute directly del 2A by del T2 from this equation. We can substitute in this equation, so we will get del 2P over del T2 is equal to EH over 2 A naught, capital A naught, small a is the radius and capital A is the area, remember, and this will be A naught over rho del 2P over del x2. So A naught and A naught are cancelled out, and we will have our equation as, maybe we will just write them and cut them. Okay, so this will be del 2P over del T2 is equal to EH over 2 rho A naught del 2P over del x2. If we compare this with the standard wave equation, we will have say in terms of del 2P over del T2 is equal to C square del 2P over del x2, and from that we will have C square is equal to EH over 2 rho A naught, where C is equal to pulse speed or the wave speed. So the speed of the pulse propagation is square root of EH over 2 rho A naught. Okay, this is what we have obtained, and then we know from our mathematics courses that how to solve a wave equation, and a solution can be found out. A similar equation can be found for u also, for the fluid velocity u. Okay, and so let us summarize what we have seen today is that laminar flow in a flexible tube, at steady state, and pulsatile flow of an inviscid fluid in a, again, flexible tube. So for the laminar flow, our objective was to obtain the steady state solution, and we can do that iteratively, but here because we had the relationship simplified, so we could obtain a relationship between A and P from solid mechanics and substitute in the Pauli flow equation, and could obtain a relationship between pressure and A, that was obtained from solid mechanics, and we also obtained relationship between the channel radius and the flow rate. So, what is the effect of the flexible tube on the channel radius or on the flow rate through the channel. For the pulsatile flow, we had assumed that the flow is or the fluid is going to be inviscid, and neglected the viscous terms in the conservation equation, momentum conservation equation, and from these equations we obtained the pulse speed. Okay. So, we will stop here. Thank you.